Okay. So let me wait for a few minutes and then we'll start. So we'll wait for a few minutes and then start. Maybe others will join. So meanwhile, if you have any queries from the last tutorial or this assignments, let's say, please ask. Okay. If there are no questions, then so let me start by reminding what we have been doing. So we have been trying to understand the topological insulator with the help of Schiffer-Higger model, right? The last lecture was almost only on understanding this Schiffer-Higger model. So there are broadly five ideas to understand this with this minimal model of SSH model. Uh, so what do we mean by topological insulator? And then band twisting, winding number. Then there's something it's called the bulk edge correspondence, or we also call it bulk boundary correspondence. And then the symmetry protected topological phases. Okay, so all these things are needed to understand why do we need a different description for understanding few insulators which are different from conventional insulator. Although in terms of band structure they're same, but there are a lot of other things that is not same uh, between this topological insulator and a trivial insulator. So in the last class, we observed that depending on this hopping of this particular SSH chain, so this was the unit cell, intra-unit cell hopping. So for intra-unit cell hopping, if it is minus T, let's say, and then there is no inter-unit cell hopping, so we got trivial insulator, and the wave function was sort of I mean trivial in a sense that it didn't had any band twisting. So if we talk about the block manifold basis, so this was the case of trivial insulator where all the block vectors corresponding to the wave function at each k was directed along a particular direction. For our case, we assume to be x, right? And then we saw another example of the same version, but then instead of intra unit cell hopping, we considered that inter unit cell hopping to be there. So so this was the trivial case, and then so this particular case was the our last I mean the case two where the so this part is the inter unit cell, sorry, in one unit cell, ith unit cell, and then this particular hopping was 0 within the unit cell, and then outside the unit cell or between two consecutive unit cell, there was some hopping of minus t. And because of this, although the bulk band structure or the in terms of band structure, they were insulator, something like this. But then we saw that there is something called band twisting, where the block vectors in the manifold was something like this, right? So in the earlier case, we had only along x direction. The wave function can be represented along the x direction at each k, but for the second case, this was directed along outward, right? And it was changing the direction as the key points are also changing. Okay. So this is something called band twisting, and this band twisting, I mean, tells us that there is something else we need to look at, and they are not really equivalent insulator. And to quantify this band twisting, okay, what we introduce something called winding number. So this was the expression of winding number, where given the wave function, you can calculate the winding number, and then you can tell that if the winding number is non-zero, that means it is non-trivial. It there will be band twisting, and that uh, predicts, or that kind of reflects that there is non-trivial topology in the system. If the winding number was zero, which was the case one, there is no band twisting. All block vector in the manifold was directed along same direction, so the system or the insulator was trivial, right? So that was the last lectures. Broadly, that's what we covered. Uh, and then the last question we aim to address, or I posed in the last lecture, is that can we go from case 1 to case 2 smoothly, right? So I have a trivial insulator, and then I also know about the topological insulator. So can I change some parameter of the Hamiltonian? So this is the theoretical way of saying it, but then experimentally, what do you say? What do you do is that you tune some parameter of the system of the material, right? It might be number density, impurity concentration in the system, or there might be other parameter in the Hamiltonian or in the material actually. So can we go from case one, trivial insulator you had, and then can you go to case two smoothly? Now, here the word smoothly means there will not be any noticeable change, and you will go to the from case 1 to case 2. Okay. Smoothly means there will not be any gap closing and gap opening phenomena, and so on, which we are going to address in today's lecture. Yeah, so that's the key question we want to address today, and there will be concept of bulk boundary correspondence and then symmetry protected topology. How the different symmetry of the materials or of the models can protect the case 2 being topological insulator, and it can remain topological insulator as long as the symmetries, there are specific symmetries of the system are intact. The moment you break those symmetries, you can go from case 1 to case 2. Okay. So that's the broad picture we are trying to understand. So if you have any question or confusion, please ask. Hello, am I audible, right?
Hi, yes, Sumit, you're audible. It's okay so far.
Okay, so things are clear, so we can go to the lecture 3 lecture. Or
Yes.
if you have any question or queries, any confusion regarding the assignments or the last lectures, etc., you can ask actually.
No, it is fine. Till now, it's fine.
Okay. Okay, so the question we are trying to understand that case 2 in a smooth way. Uh, so for this, so remember that we had the cases where I had two types of atom. So this was supposed to be my one unit cell, ith unit cell, let's say, right? And then another AB I plus 1th unit cell. So this was I plus 1th, let's say. They're same area, but yeah. So this is ith and this is I plus 1th unit cell. Okay. So in one of the cases we had this hopping, and in another of the cases we had this hopping, right? Whereas the other hoppings were not there. So what we're trying to understand, if we talk in terms of mathematics, so earlier we had this to be minus t, case one, and in the case two, so this is, let's say, case one, and this in the case two, it was this one to be minus two, right? So can we change some parameter of the Hamiltonian such that we can go from case 1 to case 2? Suppose I am changing t, okay, in a smooth way. So t was, let's say, suppose some value 0.01, and you do it 0.015 and so on. And can we go to the other limit? Okay. Okay, so to represent this combined case, what we do is that, we represent this hoppings. Oh, sorry. So this hoppings, intracell hopping to be lambda, and then there is intercell hopping to be 1 minus lambda. Okay. Okay. So what it essentially, I mean, these are the coefficients. So what we're trying to do is that, uh, so the intracell hopping strength is lambda t, lambda of minus t. So lambda is just a dimensionless coefficient, which is it goes from 0 to 1, let's say, right? 0 to 1. It can be equal to 0 and 1 also. And then intercell hopping is lambda of 1 minus t. Okay. Sorry, 1 minus lambda. 1 minus lambda of minus t. So, so when lambda is 0, so let's consider the cases. Case 1 is when lambda is not 0 actually. So when lambda is 1, then we have case 1, right? Because then intercell hopping becomes 0. 1 minus 1 is 0. And then case 2 becomes lambda is 0, right? When lambda is 0, then this part becomes 0, intracell, uh, and then intercell hopping is maximum, which is minus t. So what we are essentially asking is that I will vary the lambda from 0 to 1, and then we'll see that can we have a correspondence between the case 1 and case 2. Okay. Now the Hamiltonian we can write is that, so I'm writing the Hamiltonian directly, but this is a part of tight binding, right? Hamiltonian writing. We can read the basic books as Marvin. So this is minus t, which is hopping strength, and then you have a c k. I'm writing in the momentum space. C k a dagger, c k b, and then CKA and CKB correspond to this A type of atom and B type of atom creation operators, and then you need that hopping information. So there is no A to A hopping, so there is no on-site hopping, right? It only the hoppings are only between either A to B, so this within the unit cell, or outside the unit cell, but they are always either A to B or B to A. So there is no A to A hopping, okay? Within the unit cell also, as well as outside the unit cell, intracell. Okay, that's not we are considering here. So that's why these diagonal terms are 0. Okay. Uh, then CKA, CKB, and then if you do this, so remember that we had considered. So if I go back to the lecture 2, I'll write, then I'll explain. So this will be plus complex conjugate. Okay, so for case 1, we had that lambda equal to 1, right? And lambda equal to, and yeah, lambda equal to 1, that means that this term, so this term is going to be 0. So for case 1, we had this kind of Hamiltonian minus t, and this one, and then lambda is 1, and then this term, right? So there was no e to the power ik for case 1. So let's see what we have done last class. Just trying to correspondence so that things become more clear. So this was our Hamiltonian, okay? So this was our Hamiltonian in the case space. Let me show. Yeah. So this was a Hamiltonian in the case space. So if you write this Hamiltonian in the matrix form, so you will exactly write this minus t sum over k, this one, and then I mean CKA dagger, CKB. So this is a row matrix of two elements, and then 0, 1, 1, 0, and then this will be CKA. So this will be dagger, and then CKB. Okay, so you can write this as a so how do you prove that this is the case? Because the minus t is associated between CKA dagger and CKB, right? So uh, if you matrix multiply these matrices, so this is a 2 by 1 matrix, 2 row 1 column, and then this matrix is 2 by 2, and this particular matrix is 1 by 2, right? So you will get this single line, so this Hamiltonian. Okay, and similarly, the for case 2 we had an extra e to the power ik, so this part, right? So for case 2 we are having lambda equal to 0. Now if you go to the, so this part, then if you lambda equal to 0, this vanishes, and then there is 1 e to the power ik, right? This one. So yeah, so that way this is consistent. Now what we are interested in is that, so we have this Hamiltonian, so this we call block Hamiltonian sometimes. So HK, which is block Hamiltonian in the K space. Okay, now we want to solve the Hamiltonian, meaning we want to extract the what is will be the eigenvalues of this expression. Okay, so if you just do the eigenvalue extraction by doing the conventional, so what we do is that hk minus lambda. Okay, lambda is a bad notation here. So epsilon I 2 by 2 equal to 0, right? You solve this Hamiltonian determinant, and epsilon are the eigenvalues. So what you'll get is that epsilon as a function of k is going to be plus minus root over, uh, so you rearrange, and then you'll find that t square lambda plus 1 minus lambda cos k plus t square 1 minus sine square k. Okay, so this will be the eigenvalues. Now if we so let's separately see what is the case 1 and what is the case 2. Case 1 and then case 2, let's say. So for case 1 we had lambda equal to 0. Sorry, for case 1 actually lambda equal to 1, and for case 2 we had lambda equal to 0. Yeah, so if we put the lambda equal to 1 here, so what you will get is that epsilon k will be uh, plus minus root over t square cos square k plus this part totally vanishes, right? So I have mistaken something. Yeah, actually this should be simply t square, right? So this part vanishes, lambda equal to 1. This part also vanishes, lambda equal to 1. So this is 0. So we only have t square lambda square, but lambda is 1. So uh, plus minus t, right? So what we have essentially is that suppose this is my energy as a function of k, and then this is k. You have constant two energies. One is plus t, one is minus t. That's what we have also seen in the last lecture. Now for case 2, what we have is that, so this just means that it is consistent, right? And for case 2, you have epsilon k. If you derive it, you will again get plus minus t only. Okay. So what will happen is that if lambda equal to 0, this part is going to vanish, and then the cos square k plus sin square k is 1. So t square remains as square root of square root, then you will get plus minus t. So again, you will have epsilon of k. There are two constant energy level at plus t and minus t. Minus t energy level is the ground state, and so on. Same story follows, which is just the consistent case. Now, what happens if lambda is not 0, lambda is not 1? So somewhere between 0 and 1. Okay, so this is the case we are interested. So then we have this particular energy expression. You need to plot it numerically, or you can actually analytically also do, but yeah, essentially numerically will be much more easier to do. Now so for lambda 0 to 1, there will be some dispersion, epsilon as a function of k, so there will be some dispersion. Okay, this is not exact, but there will be some dispersion. These will not be a constant function because there is a cos square, cos k and sin k involved. Now the special case is lambda equal to 2, sorry, half. Okay, so if you see the energy at lambda equal to 2, sorry, half, you will get something like this. So small calculation I'm not doing. 1 plus cos k square uh, plus t square by 4 sine square k. Okay, so for lambda equal to half, we have this expression. Now, now when the gap closes, right? In all these cases, we are having this gap of 2t, let's say. Okay. So we want to see when gap closes, at which k point gap closes, at which point gap equal to 0. So what this necessarily means is that you have two branches of let's say energy. We call it epsilon plus minus. Plus is associated with this plus sign, and then minus is associated with minus sign. So epsilon plus minus epsilon minus is going to be 0. That means there is no gap at that k point, right? So we want to find that. So we already have lambda equal to half. Now we want to find at which k. So what is the k value? So what is the k for which this condition satisfies? Okay. So it turns out that if k equal to pi, okay. So what we have is that epsilon plus equal to, uh, so we have t square by 4, and then for cos pi, k is pi, means cos pi is minus 1, so it is 0, 1 minus 1 is 0, and then plus t square by 4 sin pi is also 0, right? So this means energy is 0 for the positive branch, and then for the negative branch, what happens? Equal to, uh, so again, so this is again 0, right? So simply it is clear from here. The whole term vanishes. So epsilon plus and epsilon minus is 0. So what we have essentially then is that, so this is my epsilon, let's say, as a function of k, and this is k, and this is, let's say, minus pi, and this is, let's say, plus pi. So this should be plus minus pi. It doesn't matter you are at plus pi or minus pi. The same conclusion will be there. So what we essentially have is that somewhere the energy will maximum, and you can calculate actually the energy will be maximum at. So this should be symmetric, but my drawing is not showing it to be symmetric. Uh, sorry. So this is pi, let's say. Okay. Uh, so at k equal to 0, you have a energy maximum, and that you can derive because at k equal to 0, we are having plus minus root square. So u square t square by 4 into 1. So this will be 1 plus 1. So 4. So again plus minus t. So that is the maximum energy that we have, right? And yeah, so that can be the maximum energy also. We have separately seen from case 1 and case 2. So this is the gap closing point, and this is also the Brillouin boundary, because for 1D case, Brillouin boundary is minus plus pi minus pi by a, right? A is the unit cell dimension, which we are throughout the lectures will consider a to be 1. Okay. Okay. So this is the case for a particular I mean lambda value, and what we are interested in is that what will be the winding number for this case, right? We saw that for case 1 winding number was 0, for case 2 winding number was 1. So for this case, remember this is the one of the midpoint case, right? So if I draw in terms of lambda value, so let's say this is lambda equal to 0 center, and this is, let's say, somewhere here lambda equal to 1. Okay, so I need to remove this. So lambda equal to 0 this case. So this particular case, lambda equal to 0 means we had uh, case 2, right? So this was case 2, topological case. And then for lambda equal to 1, we had case 1. Now we are somewhere here, lambda equal to half. And we are trying to see, so here chart number was 0. Sorry, this was chart number 1. So this was chart number 1, or the winding number 1 actually. So this particular had winding number to be 1 or minus 1, and this particular case we had winding number equal to 0. Now we're trying to find the winding number is what for this lambda equal to half case. Okay. Okay, so if you actually this has to be derived kind of from numerics. Okay, this will be very difficult to calculate a winding number analytically, because you have this kind of energy expression so this kind of energy expression, and then the wave function will also be k dependent, so it will be difficult to do it analytically. But if you do numerics and then calculate the winding number, so remember that winding number we had the formula I by pi minus pi to plus pi, and then psi of k, gradient of k, psi of k, right? And then integration of dk. So this was the winding number. If you numerically evaluate it, so something like this you will see. So this is mod of winding number. Okay. Uh, so we have something like this. So this is the lambda, and we are here at lambda equal to 1. We are here at lambda equal to 0, and this is half lambda equal to, okay. So lambda equal to 0 means we have case 2, right? Case 2 topological insulator Ti. Lambda equal to 1 means we had case 1 trivial insulator, right? And at lambda equal to half, what you see is that something interesting, because exactly at the lambda equal to half, your chart number, or actually winding number in our case, winding number changes its value. So this was constantly 1, okay, And then exactly at lambda equal to half, you have it sharply goes to zero. And then if you are lambda greater than half, then it continuously zero, even at lambda equal to one. So some special thing happens at lambda equal to half. And what is the special thing in terms of band structure? You see the band structure at lambda equal to half is gapless. Okay, so this is the band structure at lambda equal to half. It is gapless at the Brillouin zone boundary, right? At the 2 point, you have a boundary, and these are gapless because epsilon plus equal to epsilon minus. But if you are in other k points other than this particular two Brillouin zone boundary, you have a gap of this and then this and then this. It continuously decreases from k equal to zero. Okay. So you can already sense that it is almost like happening that you had some band structure like this. Okay, so so you started from this case. Let's say lambda equal to zero. So lambda equal to zero means you have this kind of band, right? A perfectly insulator. And then as you increase the lambda from zero, somewhere the dispersion comes into the picture. And then at a particular point, when you hit the lambda equal to 2, this case, you have an exact gap closing point, okay, at this Brillouin boundary. And then once you increase the lambda equal to half, I mean, increase the value of lambda from half, you again get, I mean, uh, so insulating case. So again, it goes away, okay. So again, there is a gap. So you see that you already feel that initially my system was gapped. At a particular lambda, the system gap vanishes, and then there is a again there is a gap once you cross the lambda equal to half. So there is a so this phenomena is called gap closing and opening. And what is interesting about it is that at this particular transition point, your winding number also changes sign. Okay. So if I plot in terms of winding numbers, yeah, so so now the question is, can we let me write the question and then explain. So this is the question that we want to understand. So can we connect between these two phases, case one and case two, without closing the gap? So that's what it means that then you will be able to connect these two systems or two extreme limit of our case uh, in a smooth way, right? So the moment you hit the gap closing, so this orange line here, that means there is an abrupt change in the system. You had an insulator type of type 1 and then it goes to type 2, but then in between they are not remaining insulator. At some point of time they are becoming metal, right? So if you have this kind of band structure, so this kind of band structure, right? Then it doesn't matter wherever you have Fermi energy. So if Fermi energy is here, then there will be metallic conduction. Even if the Fermi energy here at the exactly gap closing point, then also there will be metallic system, right? So the question boils down to this, that can we connect between these two phases without closing the gap? Meaning I was at insulator one phase, trivial insulator phase, let's say. Can I go to the topological insulator case without crossing the metallic regime? I'll not be having any metallic regime. We'll just smoothly go from topological insulator to uh, trivial insulator or the vice versa. Okay, in between there will not be any metallic state. So that's what we want to address, and then this will clear the other parts of the story, bulk edge correspondence, and then symmetry protected topological phase. So if you have any question, please, the central question is clear or not. Okay, so things are clear.
Sunit, the system changes its properties. Let's say from insulator it goes to metal and then to insulator. But
Right.
is it still not possible? Hello,
Yeah, yeah, I am audible.
hello.
You are audible.
Uh, okay. So the system is changing its properties, let's say from insulator to metal and then insulator. But
Right.
is it still not possible for us to tailor the Hamiltonian somehow? Let's say, as you were saying, tailor the some parameters of the system. Is it still not possible to change it smoothly so that it will go from one phase to another, or is there any block on that also? Means we cannot change some system parameters to do this
Mm-hmm.
transition.
Uh, Sorry. So let me rephrase your question if I understood correctly. Uh, okay. Okay. So the question boils down to that the fact that suppose we had a
Because
Hamiltonian.
we also talk about this, I think in the initial classes there is this talk about this adiabatic system
Mm-hmm.
and changing the Hamiltonian adiabatically. So does
Right.
this not correspond to an adiabatic change in the Hamiltonian? Like,
This you can think like an adiabatic I mean change in the system parameter, but what will turn out end of the day is that even if you change adiabatically, there will be so even if you change adiabatically, the system is not going to be there actually. So you cannot go from case one to case two even by changing the parameters adiabatically. That's what it will turn out. Okay. So, so what this
okay,
necessarily
so
means that
once
any
let's say
smooth,
you have a system that is a trivial,
right?
oh nothing, you can carry on.
Yeah. So the point is key. So the system will have some abrupt changes the moment you try to hit from trivial insulator to topological insulator. Even it doesn't matter if you do adiabatically. It turns out that the problem is not in adiabaticity. The problem is that once you do not break certain symmetries of the Hamiltonian, okay, you cannot go from trivial insulator to topological insulator. Actually, more accurate way to say this is that you cannot go from topological insulator to trivial insulator. The reason is topological insulator phase, as we will see in this class itself, that is protected by some symmetries. So unless you break those symmetries, you are not going to get into the trivial insulator phase. Case one. Okay. So although theoretically it can sound that okay, we are going from lambda equal to 0 to 1 or 1 to 0, and then we are going from one case to another case because this is the case of, so this is the picture of Poynting number. But then what problem is happening in between is that your system doesn't really remain same. It turns out that this phase had some symmetry which is already broken in this phase. Okay. So that makes it not smooth, right? This we will see. Okay.
Okay, okay, okay.
So the whole system symmetries remains gets changed actually. So that we cannot call that in a smooth way. I am transforming the system and the symmetry gets changed. It is not possible.
Okay, okay.
Okay, so for to see this how this happens and this is also called symmetry protected topological phase. Uh, so okay, so what we'll do is that yeah, okay. So let's take this case. Earlier we had this particular Hamiltonian. We had A, B, or the system actually. So this we had A, B, and then this was I think lambda, and then 1 minus lambda of t minus, and then minus lambda. So these are the hopping strength. So this was, let's say, so this was ith unit cell, and this was I plus 1th unit cell, right? So basically, what we allowed in the in this particular system, and this continues actually, okay, is that there is a hopping mismatch between the intracell hopping and intercell hopping. So intercell hopping is having 1 minus lambda t, and then intracell hopping is lambda t, and lambda is the tuning parameter that we are changing, right? So what we can consider is that uh, so instead of lambda, what we can actually do just to be more, just to make things more easy for us. So we have a type of atom. These are just parameterization. Okay, we can continue with the lambda, but the expressions will be big. So we're parameterizing it. So we had this, and then A, B. Again, we have ith and ith plus one atom, sorry, unit cell. So this we represent as T1, okay, and this part we represent as T2, and this one continues, okay. So we'll have somewhere here A, and then somewhere at B. Again, this part will be T2, and this one will be T1. So intra-unit cell hopping is equivalent to T1, and inter-unit cell hopping is T2. So what this then the ratio of T1 by T2 or T2 by T1 is going to determine which case I am in, right? So earlier we are considering the, I mean, extreme cases. So T1 by T2, let's say. So when T2 is 0, or rather make it T2 by T1. So when T2 is 0, we had the case of, let's say, case 1. And then when T1 was 0, we had case 2, right? Okay, so instead of this, I mean, instead of lambda, we have represented by T1, and what happened in our case, so the special point for us was this point, lambda equal to half, and lambda equal to half essentially means T1 equal to T2, right? Because our hopping strength, if you see here, uh, so yeah, so if you see this part, right? So lambda equal to half means you had this part to be minus t by 2, and this part will also to be minus t by 2, right? So the intracell and intercell hopping, uh, they becomes equal when lambda equal to half. So this was the case we considered, and we have seen that if you calculate the winding number exactly at the lambda equal to half, you will have a jump from finite winding number to zero winding number. So this we have studied so far. Now let's add another term in the Hamiltonian, okay? In the Hamiltonian or the system. So what we are doing here, so remember that earlier our Hamiltonian was K Hamiltonian was 0, and then 1, so lambda minus t was there in front of it, plus 1 minus lambda e to the power ik, or it was minus here, and then lambda plus 1 minus lambda e to the power ik 0, right? So this was the Hamiltonian in the earlier case. Now remember that this 2 was 0. The diagonal terms were 0. So what this necessarily means is that we didn't allow this hopping from A to A, hopping is 0. So this was not allowed earlier cases. And this term can be non-zero even when there is some potential term, right? So there is a on-site potential, we call it. So what this necessarily means is that at each site, electrons feels some amount of potential. Okay, so during this transition from A to B, they are having hopping strength of T1. But even when the electrons are at exactly at their corresponding atom, they also feel some energy. So if we consider this, and not only that, so we what we consider is that electrons at A type of atom feels m energy, let's say, and electrons at B type of atom feels minus m energy. Okay. Okay. So if we consider this, then so the Hamiltonians becomes this m lambda plus 1 minus lambda e to the power minus ik, and then this will be minus m. So this is in the A B basis. lambda plus 1 minus lambda e to the power plus ik, right? So suppose we considered a case where the both these terms were plus n, right? So then what will happen is that, so let's call it equation 1, let's call it equation 2. So then if A type of atom and B type of atom both filled the same amount of m, then what will happen is just the equation of 1, let's say, right? So this Hamiltonian, and then plus m, this is identity matrix, 2 cross 2 identity matrix. So at the same energy, I mean the same energy getting filled, meaning here also m, here also m. But this constant energy, so this constant energy you can always kind of I mean extract out, right? So earlier you had this kind of energy structure. This was plus t, this was minus t, but then because of adding the mass term, what we are having essentially is that this and this, okay, the equal amount shift. But this is not going to change anything actually, okay? This is not an interesting case that you are shifting all the energy levels by some, I mean, uh, constant amount. That's not an interesting case because you can actually effectively write this Hamiltonian as hk minus m uh, unit matrix 2 by 2 is to be hk of 1, and then you can call it this to be hk effective, right? And the everything follows out actually. So there is nothing interesting about that. You can always any physical problem, you can theoretically at least think of that. I can shift the uh, whole energy levels by the constant amount and the physics doesn't change. So this case is not interesting. It is the same actually. It's not interesting, that is not true, but same as mass equal to 0. Okay, we are just shifting the whole system with some constant energy. But what is interesting for us is this one. Okay, equation 2 is interesting, where a type of electrons at the a type of atom fills the energy of m, at the b type of atom it fills the energy of minus m. Okay, so let's see what happens. Okay, so if you solve this equation, or rather I am talking about T1 and T2. So I, instead of lambda, I am using the I will use the Hamiltonian T1 in terms of T1 and T2. Okay, this is just to write the expression more compactly, nothing else. T2 e to the power minus ik, and then T1 plus T2 e to the power plus ik and minus m, right? So again, you will find energy in terms of k will be plus minus m square plus t1 plus t2 cos k whole square plus t2 square sine square k. Okay, so this is the energy expression. Now, what is so interesting about this particular problem is that now if you calculate, again you need to calculate the winding number numerically, because this is the energy expression and you need to put this energy and then solve the eigenvalue problem to get psi k plus and minus, right, corresponding wave function. So this will be fairly complicated, and if you numerically evaluate this, I mean the winding number, okay, so what you will see is that what you're interested. So I am plotting now somewhere here. So this was my, I mean, okay, so this is my T2 by T1 case, right? So when T2 is 0, that means we are in the case 1, trivial insulator. So let's see in this model. So here, when T2 is 0, that means there is no uh, inter-unit cell hopping, right? So inter-unit cell hopping is 0. So that means we go back to the trivial case. So in the trivial case, we had the winding number to be 0, right? So what we have is that T2 is 0. So this we started from 0 and then this goes to infinity. Okay. So this T2 goes to 0 means we have a winding number to be 0. So this is the case where winding number, mod of winding number is 0. And when T1 is greater than T2, right? So this was the case. Uh, so this was the case where we had mod of winding number to be non-zero at least. Okay. And there is a special point here correspondence to our lambda equal to half case that we considered, which is gapless, right? So, so here it is trivial insulator. Here it is topological insulator. And this is the gapless point, point, let's say, or gapless case actually. Now, we have also drawn another axis along this, which is m by t1. The m is called usually called the mass term. Okay, and so this was the case. So this here also m by t1 is 0 at this point, right? So this was the earlier case that we consider where when m equal to 0. Now, when m is there, that means we are somewhere here, any point which is not lying on this particular axis. Okay. So if m is finite, that means we are already up here. So from here to we already went there, depending on the value of m. But we are not on the this axis. Okay. And so these are numerical results one has to calculate. Okay. What I'm trying to tell is that the physics wise the result you will get and what that does it mean in terms of uh, topology and so on. Okay. So yeah, so the question is, so what we have seen earlier is that if you are sitting here exactly at this point, let me use a different color. Uh, so if you are exactly at this point, so you had no m mass term, then uh, so here to here, going from trivial insulator to topological insulator was not possible. Okay, without I mean, so this was not possible because you hit the gapless phase. Okay, so this particular phase you hit, and then the all the smoothness and continuous tuning of the parameters, things like that, all story went away. Okay, now what we are interesting or asking here is that if I am here already, let's say I am not exactly at the 0 point, rather I am here, okay, with some finite mass. Can I go from here to here smoothly? Okay, so to answer this question, so and it turns out that yes, it is possible. So along this path, it was not possible as long as you have m equal to 0. But along this path, it is possible, and we'll try to understand why this is possible, and that we understand in terms of symmetry. Okay, so let's talk about some symmetries that our Hamiltonian have. Okay, okay, so. Now, this is a numerical result. I am once again emphasize that once you consider M1 and then change the parameter T2 to T1, what you will see is that in terms of band structure, what you'll notice is that suppose, let me, sorry, it's not responding. So what is really happening with some finite m is that you had some, let's say, energy of k, which is also a function of m because you have a m here, and then as a function of k, let's say. So if you calculate the energy plus minus energy minus, what you see and from this expression. is that you will always have some or the other, I mean, the system will always be gapped. Okay. So this terms were, so initially what was happening is that at some particular value of lambda, or in our case it will be, in this case it will be ratio of T1 by T2, or T2, sorry, T2 by T1. What was happening is that gap was getting closed, right? Epsilon plus was getting going to epsilon minus. But then as long as you have some m not equal to 0, then irrespective of any value of T1 and T2 and any value of k, you will always have epsilon plus to be, let's say, plus m, epsilon minus to be minus m. Okay, so this is always guaranteed. Yeah, for all, I mean, okay. So what I'm trying to say is that, so it is happening in terms of, let's say, if I draw the picture. So earlier we had something like this, right, at a particular lambda. So this case was lambda equal to half, and this was Brillouin boundaries minus pi by a was equal to 1. And now if you draw this, what we'll see is that, so, okay, so this will be the case, and so this part, this particular energy is m, and this particular energy minus m. Okay, so at any point you are not closing the gap. Okay, so the system always remains insulated. And when we talk about this going from trivial to, let's say, uh, I mean, topological, if you're following this particular path at finite m, the system always remains insulated, and then it is transitioning. Okay, and then then we want to study the what symmetry this m term breaks and how it allows it. Okay, so what we have in our Hamiltonian, let's say, symmetry. So first thing we have, you can check this Hamiltonian actually. So this, but I'm talking about this Hamiltonian. Okay, so let's take it uh, case, I mean, equation 3. Uh, so hk equal to h of star. Star means complex conjugate, h of minus k. And once this condition satisfies, we say that time reversal symmetry is there. Okay. Case 2, or the other symmetry is that if m equal to 0, what it happens is that then the Hamiltonian forms looks like this is 0, this is 0, there is some number here, there is some number here. And if we have the Hamiltonian of this form where the diagonal terms are 0, so this particular symmetry is called chiral symmetry. I'm not going into the very detail of these symmetries, but the minimal which we need to understand. Okay. And also, so there is another symmetry which is something called charge conjugation. And charge conjugation mathematically can be represented properly by Ci daggers, or let's say, so mathematically represented by Cka daggers goes to Cka, and then Ckb dagger goes to C of minus k and b. Okay, sorry, this will be minus k. So this is the charge, or the vice versa of it. Okay, so uh, you can make that Ck dagger goes to minus of Ck minus k, and then vice versa, or the vice versa. Okay, So this is actually a combination. Charge conjugation is combination of time reversal symmetry TRS. So let me write here TRS uh, plus this chiral symmetry, and chiral symmetry we represent by S. Okay, so TRS plus S is there, that means charge conjugation. Now these are two mathematical. So how do you see that a band structure have a or the electrons are having a charge conjugation symmetry? You look at the band structure. These are easy way to understand, but mathematically rigorous way, of course, this definition is there, and the more general version of it. So you see energy versus K, right? And if they are particle hole symmetric, meaning suppose I have a band structure like this, and then exact copy of this is also there below energy. So this is the zero. So along this is positive energy. Along this is negative energy. So if this part is exactly copied here, just flipped, okay, that means we have a charge conjugation symmetry, or more in more simple words, we sometimes also call particle hole symmetry. Okay, so this is the easier way to understand it. Okay, now there is something called symmetry classes and so on. There is one lecture I think in the week one itself that Satold, I mean, delivered a long lecture. But we're not going into the details. But what is important is that in our Hamiltonian with m equal to 0, okay, so m equal to 0 means anyway m doesn't break time reversal symmetry, so we already have this time reversal symmetry in our Hamiltonian. When m equal to 0, then we have chiral symmetry, and then even with when m equal to 0, we also have charge conjugation symmetry. Okay, so if these three symmetries are there, so if m equal to 0, we have something called TRS symmetry in the system or in the Hamiltonian, because system is represented by Hamiltonian. We also have charge conjugation symmetry. Okay, and we also have sublattice symmetry or the chiral symmetry. So once these three symmetries are there in a system, if in a system the three symmetries are there, what we call this is that BDI symmetry class. Okay, so these are some named by some scientists. I actually forgot the name of the main people who invented it. But and then later it was revised and extensively studied, and I mean developed by other people also, but there is one people. So if these are the symmetries, then we have BDI symmetry class. Okay, so there is a nomenclature all involved and associated tenfold symmetry classification and so on, but we're not going into the details. But if m equal to 0, let's say, okay, if m equal to m equal to 0, then this chiral symmetry is gone, or the sublattice symmetry is gone. So sublattice or chiral symmetry is no more. Okay. Uh, and also because the charge charge conjugation symmetry is equivalent to time reversal symmetry, and then plus you cannot write this as a plus. Okay, symmetries are the elements of a group. By group I mean mathematical groups actually. But for simplicity, we are just writing TRS plus sublattice symmetry or the chiral symmetry. So this symmetry is gone. That means charge conjugation is also gone. Okay. So if m not equal to 0. Now let's see. Let's just understand why m not equal to 0. Sorry, this will be not equal to. M not equal to 0 breaks this chiral symmetry or the sublattice symmetry. Of course, the Hamiltonian gets this m and then minus m, and then there was a this terms t1, t2, and to the power ik and so on. So this is not 0, but rather function of t1, t2, and k, and then f star here, right? So once these type of terms comes, then it is already gone. But then if we physically, intuitively want to think of, then we had A type of atom, we had B type of atom, and this was the unit cell, let's say, and then there was another A and B and so on, right? It continued. So what we have introduced here is that here there is a energy M and here there is a minus M, right? And given that this unit cell is consist of two types of atom A and B, we can think of that the whole unit cell is consist of two lattices. I mean the lattice is consist of the whole unit cell, this one, right? But then one unit cell is also consist of one kind of sublattice, we can say. So we can kind this is thinking. So this is one sublattice consisting of A type of atom, and then there is another sublattice consisting of B type of atom. Now earlier, what we had is that complete equivalence. So you had a this particular, I mean, hopping probability to be T1, and then from B to A it was also T1. But now what you have is that electrons are filling extra M if they are at A type of atom, but electrons are filling minus M if they are at B type of atom. So the equivalence between the A and B type of atom is gone. Okay. In other words, the equivalence between two sublattice. So this is one sublattice and this is another sublattice within a unit cell is gone once you introduce different mass term. So that's why we call it sublattice symmetry. Okay, that's the easier way to think. Now, what I'm trying to say is that if this m not equal to 0, then the system do not have chiral symmetry as well as system do not have any charge conjugation symmetry as well. Now, if this is the case, then what we call is that sorry. So if we do not have this symmetries, then we call it class A1. Okay, so this is the A1 class symmetry. So we can actually simply we represent it as TCS. C means charge conjugation, T is time reversal symmetry, and S is chiral. Okay, so TC here was equivalent to 111. So 111 means time reversal symmetry was there, charge conjugation was there, chiral was there. In this case, we represent it as TCS equivalent to 100, right? So time reversal is there, but then charge conjugation is not there, chiral is not there, so 00. So what really happens is that the system now if we redraw this diagram, so this particular, okay, so this m versus T2 by T1, and then see the winding numbers. So what we have is that we have some, okay, I don't need this, some finite m, and there is some transition point. So this was winding number 0 case, trivial, and then this was topological. Okay, mod winding number to be non-zero or 1, let's say in our case. uh, what is most important is that what we have seen here is that along this line, so how do I represent, so along this line system was in the class BDI. Okay, just remember that if time reversal, charge conjugation, and chiral symmetry was there, we said that this system falls into the BDI class of symmetry or BDI symmetry class. Now anywhere you are not in the along this line, so anywhere here, okay, highlighted by yellow, I just need to avoid the m equal to 0 point, just that. So all of these lines of different colors, so all of this line excluding m equal to 0, the system falls into the class A1. Okay, so what this necessarily means is that if you are at m equal to 0, your system falls into the class BDI. And once you are in the BDI class, you cannot go from topological. You started from somewhere here. You cannot go from topological to trivial case without closing the gap. Remember, this was the gap closing uh, point, right? So you had a topological insulator, and then you are changing the system parameter. You hit the topological gap closing point, and you went to the trivial. But the moment you hit the gap closing point, you are not changing the system parameter smoothly. You have some change in the whole yeah, okay. But if you are somewhere here, not at m equal to 0, if your system has that kind of Hamiltonian or that kind of terms, then you are good to go from topological to trivial and so on and so forth, because the whole class of the symmetric class of the material changes. So what this means is that BDI's class of symmetry or BDI symmetry class protects the topological uh, state of the matter, as long as you do not change the system parameter uh, such that there is a gap closing and so on and so forth. Okay, is the concept clear? Please ask questions. This is a very important point. So key point is that one cannot go from topological to trivial if sorry if BDI symmetry is kept or protected. Okay, so this implies that once you are in the BDI symmetric class, this is referred to as symmetry protected topological phases. Okay, okay. So any questions? Please ask. Any part of the lecture is not clear, or any questions? So no questions. Okay. Okay. So that was the story about topological phases and its protection under symmetry. And yeah,
Sunil,
yeah.
uh, so let's say we have this topological insulator class for both these cases, one system in BDI symmetry class and the other in system in AI symmetry class.
Hmm.
So is there any difference to these two systems, like physically, like whether
Yeah,
it's in one symmetry?
yeah. So one is that the difference is, of course, in terms of how can you go from topological to trivial case as you change the system parameter. Okay. Uh, so what is really, so these are just Troy model to understand the physics of it. Okay. So in the realistic system, what happens is that uh, uh, so if you are in the topological system, uh, so you have some material, let's say, okay, and you are in the BDI class of material. Then what you will have is that you are in the topological system, topological phase. Your system is going to be topological unless you change the system parameter or material in such a way that the whole symmetry class gets violated. Okay, and this is important because if we do not change the system in a very drastic way, your topological state is going to be protected. So you can do lot of measurements, and sometimes people are interested in quantum computation and so on. So they are also be protected. The system properties is going to be protected as long as the symmetries are not broken. If you change the
So
symmetry,
those systems would be BDI class. Means the more useful systems will be the BDI class
yes,
systems.
yes. And this is
Okay. Okay.
one of the cases actually. Okay, so there is a tenfold classification. There are many other terms, or there are many other symmetry classes. It turns out that if these three symmetries are there, there are actually other symmetries which are not talking about. But if these three symmetry, time reversal, charge conjugation, and chiral, it falls to BDI class. And then only time reversal, only but then there is no charge conjugation, there is no chiral or sublattice symmetry, it falls to AI. But then if you, as you can see, that there might be other combination, right? I do not have time reversal symmetry but have chiral or sublattice. If that is the case, then there is another symmetry class, and so on and so forth. But yeah, from a practical perspective, BDI class is more interesting because it protects the fields. Okay. Yeah.
Okay.
Yeah. Okay, so now, so this is a, I mean, so we are saying that, okay, you cannot connect it from one state to another state, uh, I mean, in terms of winding number and so on. And let's again remember that one of the ways we differentiated before calculating the winding number was this, right? So we had a block vector, I mean the wave function. This was psi in a block manifold, kx and ky space. In the trivial case, we had all block vector. So this was our psi k at different, sorry, yeah. So this was our psi k at different k points, right? And then we are seeing that is it parallel to along x? Can it be represented like that? What we had seen in the earlier class, in the trivial case, this was always parallel to x or along some direction. For the non-trivial case, we had uh, so this was outward, right? So if we think from this perspective as well, that you draw the block vector and then try to see if we can go. So essentially what we are having is that you have two cases, right? One case is that let me use different colors. So one case you had uh, so it's disturbing. So one case you had this particular system, you had a trivial, right? And then another case you had so this was the case, right? And we have been saying again and again that you cannot go from here to here uh, without opening up, or without closing the gap, right? So so if you see from this perspective as well, from this figure as well, so suppose you had this particular figure, right? So can you smoothly change these arrows so that this arrow at this particular point actually points out outward? Can you smoothly change something? Meaning you have this in the within the plane, you had arrow looking like this, right? And then you want to make arrows like this. Okay, so it turns out this is not allowed. I mean, continuously you can rotate, but within the plane also, so what will happen is that so yeah, so let me draw it and then explain. So you have this, and then So it's very difficult to draw here, but okay. So what we're trying to understand is that uh, so earlier you had this along this line, right? Now smoothly changing these vector arrows, you cannot go this state. Okay, so here to here is you cannot really go. Okay, and remain you have to remain within the plane itself. Now you can rotate these vectors, but that will change the state itself. Okay, now when we have m not equal to 0, so m not equal to 0 case, let's say. Now what really happens is that earlier we have seen in the last lecture that if you have bz equal to 0, right? So if I go to the last lecture, if I had bz equal to 0, so yeah, so this part is the case, right? So we considered a general Hamiltonian like this, and where the wave function, general wave function was this, and then we assume something that if we have bx to, so we mapped this Hamiltonian actually. So we mapped this particular Hamiltonian equation one. Equation one represents the spin in presence of a magnetic field in a 3D space. Okay, the spherical coordinate space, and then we map this particular in that particular Hamiltonian to this, right? We had a the case of topological case where we found that bx was something, by was also 0, and bz was also 0. If we had the trivial case one is bz is 0, bx is minus t, by is 0. For case 2, what we found is that bx and by had some finite value, right? X and y had finite value, but yet bz was also 0 somewhere here. So somewhere theta needs to be 0 actually. Uh, no, so here is cos theta, that means cos theta needs to be 0. So cos theta is 0, that means the magnetic field is, sorry, cos theta is 0, that means it is theta is pi by 2. So that was the case for non-trivial case as well, right? Uh, So cos theta was pi by 2. So the vector manifold was only in the in plane, right? Theta was already pi by 2, and then we had a different phi value, and depending on the phi value, which represents the each k point, right, within the 2D plane, we had this particular structure. Now, what really happens when you have Bz not equal to 0 or m not equal to 0 in our case? Okay, so if you look at this Hamiltonian once again, so we had, so this particular equation 3. Okay, so if you look at equation 3 and then the general spin Hamiltonian we considered, so this equation 1, you see that cos theta was representing, b cos theta was representing the z component of the b, right? If you see this equation, I mean this spherical polar coordinate. Now introducing m essentially means your vector can also be now out of plane, because b has a bz is not equal to 0 effectively, right? So yeah, so bz is not equal to 0 here, and or m not equal to 0 means bz is not equal to 0. So what your spin can do is that they were along this direction for case trivial case, but they can go out of plane. So this is in the xy plane, so this is in the xy plane, and these particular, although it is not represented properly, but these spins represents, let's say, out of plane movement of that. Okay, out of plane. So you just need to visualize it, because in 2D we are not really able to properly represent it. But your so the vectors were along this direction, and then suddenly once you introduce this m not equal to 0, there is a bz, kind of bz is component is non-zero. What that means is that your spins from x direction, or let's say along this direction, it can go out of plane and then come back to the plane. Okay, so that this particular configuration gets created. And this was for the topological case. Okay. So the vector manifold, so this vector manifold can change now smoothly. Once you have finite M, this vector manifold can, as the vectors can go out of plane along the z direction, so they can smoothly change and then reorient themselves in such a way that this particular configuration gets created so that they are out of plane and then the system is topological. So this also explains that if you, even if you think in terms of this block manifold picture, that in our in m equal to 0 case, so going from this to this case was not possible because there was no smooth way of changing these vectors, parallel vectors to this outward vectors. Okay, but once you have m equal to 0, the spins, these parallel spins can go out of plane, so they can move from xy plane to z direction, and then they can reorient them back themselves into the xy direction, and this becomes a smooth way of transformation. But then you already broke the symmetry classes. Okay, so that's just another way of seeing this, that if you protect the symmetry, no smooth transformation can be done from going this state to this state. But if you break the symmetry classes, then you can smoothly go back to in between these two cases. But the cost you are paying is that this particular topological phase is not protected. So that's the scenario. Okay, so what we have covered so far is that how topology is different. I mean, topology determines the difference between a trivial insulator and some special insulator. But we have still not talked much about its experimental consequences, right? We are almost mostly on the theoretical side, that how do you distinguish between these two? You calculate the winding number, and what does it really represent? How these phases are protected under some symmetry, and so on. The so the experimentally what you find is that, of course, as I have said, if you have a anomalous Hall insulator or topological insulator, which also breaks time reversal symmetry, what you get is that you get edged current, or I mean Hall current, even though your bulk is gapped. Okay, and this is called bulk boundary correspondence, that your edge of the sample, or the physical boundary of the sample, any physical system you consider in the laboratory are definitely finite, right? So although the bulk is gapped insulator, but then physical edge of the sample carries current so that you get some Hall response. So in the remaining time, we want to understand a little bit of that actually. Okay, what we call bulk boundary correspondence, and how the edge state appears, and what are the features of it. Okay. Okay, so any questions? Okay, okay, so let me start. I mean, go to the bulk boundary correspondence then. Okay, so far we are considering, this understanding this bulk boundary corresponding is easier when you consider the open boundary chain, sorry, open chain. Okay, so earlier we are considering that, let's say we have a type of atom and then B type of atom, and then there is, this is the unit cell, and then another atom, another unit cell A and B, and so on. We are continuously saying that this part basically goes on in both directions. Now what we are considering, or what we are trying to understand, let's consider case 1 and 2 as an open chain. So they are finite. So let's say we have A type of atom, B type of atom, and these are connected. So these are unit cell, ith unit cell, right? And this is I plus 1, and this goes on. Now instead of considering the infinite case, what we are considering is that system is bounded. Okay, it has a finite length. There are other, yeah. So that is the case. Uh, so this was case one. So what we had is that trivial insulator, right? We already know that there is only intra-unit cell hopping T1, and there is nothing here. So this was trivial insulator case 2. Now we consider is that again we are going to the extreme limit, what we have studied in the last class. This will help in understanding. So A, B, then A, B. So we had this to be ith unit cell, but then within the unit cell there is nothing. Well, I mean no hopping. And then in between the unit cell, inter-unit cell hopping was T, yeah, T. Let's represent simply by T. No T1, T2, because we are in the extreme case, so better is just T. And then this was also T. Okay. So let me represent as it is. So these are unit cell, solid line means unit cell, and then T are the inter-unit cell hopping. And this was the topological case, topological insulator. Now, if we look at this, the energy spectrum of these two again, okay, so what will happen for case one, let's say, for trivial case, what will happen is that, so these will be energy levels. Again, I am going to the real space, okay, depending on the number of unit cell, we'll have a different energy levels, and this will be plus T, and this will be minus T, right? So this we have done in previous classes. And there is 2T of gap, and this is trivial. If we draw so this was for case one, okay, so this one for case two, what will happen is that again we will have some energy levels, discrete energy levels, right? Again same story, plus T minus T. Okay, so let me draw one less. Actually I have drawn three unit cells, so let me draw three here, but in general it can be extended. So let me draw three, and then here only two. Okay. Okay, so this is plus T, this is minus T. And here comes the important point, that at the zero energy, there are two states. So this is energy equal to zero. Again, this is also energy equal to zero. So depending on the number of unit cell we have, we are considering single orbital and so on. So earlier in this case, I mean, case one, we had three unit cell, right? Three we have drawn just. So there are three energy levels, and in each unit cell can contain plus and minus energy levels, right? Plus T and minus T, just because the electron can be here or here within the unit cell, right? So there are two I mean energy level corresponding to each of the unit cell. So I have drawn three unit cells, so three up and three down, or three plus T and three minus T. So I have done this part also, three unit cell for the topological case also, but what really happens is that now these contributes to the, sorry, what did I do? Yeah. So these particular things contributes to the energy levels, right? So earlier we had how many T? So if I draw, let me draw it. So within the unit cell, so this was another T, this was another T. So three hopping was there intra-unit cell. So ultimately we had six energy levels, right? Now here the hopping numbers are here one and then another two. So that's why they corresponding to four. Two plus T and two minus T. Now the important point is that here the electrons at A and this B. Okay. So these 2 points, the electron feels no energy. Why? We have not considered on-site energy, right? Electron feels energy, or electron, it costs only energy. Energically, it is costing only when it is going from A to B or B to A. But if the electron feels sits at A or B type of atom, then it feels no energy. What does that mean? Is that we have energy levels exactly at the zero energy. Okay, so this is called zero mode. So two energy states. So let me write zero energy. Okay, and this is called zero energy modes. Now for the trivial case, again case one, let's say for the trivial one. So trivial case, we have unique ground state, right? Unique ground state, because let's say you fill the electrons, right? And you are trying to half fill the system. Okay, we are always interested in the half fill. So what we'll do is that electrons will come and then sit here, here, here. You are done. Again, remember that spin is not in consideration. So we have a total six state, and we want to fill by half. I mean half filling case. So we need to bring sorry, three electrons. So three electrons sit in the lowest energy state, ground state. Okay, and you're done. Unique ground state. Now, what is interesting for the case two, topological case, suppose you want to fill half fill the states, right? So topological, two ground states. Okay, so in the previous case we had a unique ground state, but the topological case we have a trivial ground state. Sorry, two ground state. And how do we understand that? Because remember that we had a zero energy here, two zero modes here. So if I draw here the zero energy modes, so suppose so these are the physical end of the chain. So let me draw it in a larger way. Uh, okay, so if you correspond this actually, so the here we had a this case and this case, right? So what we are having is that electron can sit here or here. It depends. So electron can sit here or here. Again, so what do you mean by half filling? We have total six energy state here also, right? The number of atoms are same, so the energy states have to be the same. So we have total six energy state in the topological case as well. But the only point is that we had two minus T energy state, two plus T energy state, and two energy state exactly sitting at energy equal to zero. Okay. Now you are trying to half fill the system. So again, you bring three electrons in the system. So you one electron is there. So two state is filled, no problem. But then there comes the dilemma that your electrons can be here or here, right? In either of these zero modes. So that's why we have a two ground state in the topological case. Okay. So what will be happening? So what this physically means is that you can add an electron here when you are trying to half fill the system, or you can add an electron here, and it will cost no energy to you. It can just be there. Okay. Okay. So basically the point is you can add an electron to either physical boundary, I mean right end of the system, or the left end of the system actually. Okay. Okay, so there are many much more mathematical ways to see this, and these are the age state actually. So what this gives rise to is that so what people does is that so they construct this kind of Hamiltonian, okay? I mean this kind of discrete semi-infinite Hamiltonian or basically finite Hamiltonian. They construct the Hamiltonian in the real space with let's say n number of unit cell. Okay, n is some finite number, and they see that how the wave function of the end. Okay, so I am assigning some number, right? N is the number of unit cell, then we'll have, let's say, starting from, so for our easy to use, we're starting from, let's say, n, and then we go to n plus 1, and then so on, n plus n, let's say, right? These are just numbering of the unit cell. So what people see is that they determine the wave function for these two edges, actually. Okay. So this can be done mathematically, and for our case also, partially it can be done analytically, but not full solution will be there. But what people see is that something like this happens. So suppose you are plotting the wave function of the nth, and remember that this is the physical edge of the sample, one edge of the sample. Let's say left edge, right? What people see is that, and we are plotting Na square wave function corresponding to the electrons at the atom at the, I mean, left end of the atom, and they are plotting the wave function as a function of, let's say, site number I, or we are representing by n, so n, right? What people notice is that exactly at this point, so exactly, so this is, let's say, nth atom, and then it increases, okay? And it increases, it goes to n plus n somewhere, because that's the another boundary where we are having n number of units. So what people notice is that this edge state corresponding to, so how do you do it actually? So the algorithm is pretty simple. You have Hamiltonian, right? And you write A and B, A and B, A and B, because that's how the system is, right? You have a finite system, so you consider each unit cell, A and B type of atom, and depending on the case, you are in trivial or topological, you I mean put the hopping term correspondingly, and you diagonalize the Hamiltonian. There are tools to diagonalize in any programming system, and then once you diagonalize the system, you can also get the two things you immediately get. One is energy. So if the Hamiltonian is n by n, let's say, right, you get n number of energy eigenvalues, and then the corresponding wave function. Okay, and then you see the, I mean, you can actually extract out the energy wave function corresponding to the energy zero, let's say, because that's where we are interested in, right? Zero mode. So, and then you plot this wave function as a site number. Okay. As you increase the number of sites, or n you increase, and how does the wave function behave? What you see is that they exponentially, so this is a function, this is roughly goes as, okay, approximately goes as minus n xi. Xi is some length scale. Okay. So they live on the physical edge. Remember, n is the physical edge of the sample, and as you go into the bulk of the system, the wave function exponentially falls off. Okay, okay. So what this tells us is that this zero energy state, what we are talking about. So these zero energy states live on the edge of the sample, and that's why we call it edge states. Okay, whereas for trivial system, you will not have any edge state in the sample. For the non-trivial case, topological case, you will have a edge state which are having zero energy, and they can conduct the electricity or Hall response, and then give rise to some uh, I mean non-trivial response. And this is the reason why people say that, sorry, the bulk is gap. So remember the we have a gap here, right? The bulk is still 2T. The difference in energy between up I mean down band and up band is 2T. But then there are particularly two states where they have a zero energy, and once you numerically solve this, you see that the zero energy states, which we denote by psi na square. So this is the probability, right? Wave function square. You see they live on the edge. So nth is the one of the edged atom, and as you go within the bulk within the sample system, so this should not be n plus n actually. Okay, yeah, some n, and then somewhere here, let's say n plus n. Okay, now as you go within the bulk physically means you are let's say so you're trying to see the wave function here. Okay, and these zero energy modes, you will see that energy wave function, zero energy modes wave function peaks here. Okay, uh, and then so basically they peaks here and then it quickly falls off as you go I mean within the sample. Okay, so this is called bulk, I mean edge modes. So what we learned is that there is edge state, and similarly there will be edge state at the left end, sorry, right end also, right? So we have drawn from the left end and then right end also it will be there. Okay, so there is edge state in the topological insulator with zero energy, and they live on, or they localize at the physical edge, or rather boundary of chain, or you can call it system. Okay, so again we're trying to understand what is the difference between the topological insulator and trivial insulator. So trivial insulator is not having any zero energy modes, it is not having any zero energy states, and this you can again verify numerically. Okay, so if you plot that I mean plot the case for trivial insulator, you will not get any uh, here. Okay, so they will somewhere be picked at only at the bulk state, but they will not be picked at the edge state, I mean at the physical boundary of the system. Okay, so what we find is that so there is a difference to insulators which manifest on the of the system, right? Now let me draw the figure again, drawing again and again, but this is always important for clearing the concepts or easy to remember. So somewhere here you hit the gap closing point, right? You hit the metal basically. Gap closing means metal. So you are in the topological insulator regime, topological insulator, and you are in the trivial insulator. So this is T2 by T1, right? Uh, or no, sorry, this should be T1 by T2 because when T2 is greater than T1, we saw that this is the case, topological case. And along this particular regime, as long as you are in the topological case, id state exists. And in this regime, so the whole regime, let me, no id state. Okay. So the key conclusion is that topological, what do we mean by topological bulk is that the system is, I mean, if you consider the bulk wave function, so earlier we are calculating the bulk wave function, right? So in the topology, so this case actually, so we calculated somewhere wave function. I mean, we have not yeah, this was the case, right? So these we calculated the wave function for this was for case one and for case two. So these are all bulk, and we assume that the system is infinite periodic, so we can calculate the wave function, assuming the Hamiltonian is also periodic and block wave function basically. Okay, so what we're trying to say is that topological bulk leads to non-trivial physics or edge state at the boundary of the sample. Okay, and this is called, people also call it bulk edge correspondence, but edge and boundary are synonyms, right? So if you actually numerically evaluate and so on and so forth, which we are not going to do, of course, what you'll see is that in a realistic system, if you have given any Hamiltonian, you will see some bulk state, bulk energy state, depending on the number of sites you take. So these are bulk energy states. And interestingly, you will see that there are some energy states which goes like this. Okay, so this will go like this, and this is energy equal to 0. So if you calculate numeric, so these are the bulk energy states. So this is also bulk, and then this is the edge. Okay, so this was the story of bulk boundary correspondence and symmetry protected topological phases. And one final point I want to emphasize that in both the lectures, in the last lecture as well as this lecture, you see one of the most important thing which is coming again and again when distinguishing between the trivial state and the topological state is how the wave function look like, right? In the last lecture also we have seen that there is a, I mean, the vectors are along the same direction, block vectors are along the same direction basically. Uh, for the trivial case, and then there was some non-trivialness. I mean, they are outward for the topological case. Today we saw that even when we consider about, I mean, the finite chain, the last class was always about the periodic case, infinite system, periodic boundary condition you can impose. Uh, so, so basically, that was the case previously. Now we considered towards the second half of this lecture, we have considered a finite chain and we have tried to see the difference between this trivial case and the topological case, right? Let me write topological. So trivial and topological, and in terms of energy, the only difference for the finite and the boundary. So there are 2 3 points that we want to summarize. In the periodic case, the energy eigenstate, so this energy eigenstate for the topological and the trivial was exactly same, right? That was the topic of yesterday, I mean, the last class. So the energy eigenstate were exactly like this for both the cases in the periodic boundary condition or the infinite case. Once you consider finite chain, so the system has a physical age, they are not infinite. If you are in the trivial case, then again things looks very similar to the periodic case. But if you are in the topological limit, you have a finite edge at the sample, and then what you see is that along with the conventional, I mean, energy bands, there are two extra energy, not extra, but two energy actually lives in the zero energy state. So the energy spectrum also do not like looks like the same, right? Once you go to the finite chain limit. So that's the first difference between periodic and finite chain limit for the topological and trivial cases. Okay. And then the second difference that we saw, or yeah, I mean, I just mentioned, I have not proved because these things needs to be numerically evaluated, is that for bulk case, I mean, sorry, for this finite case, if you are in the trivial, so that you see that wave function will be picked at those sites, A and B sites, okay? And they live always mostly live on the bulk of the sample. By bulk, I mean the not on the physical edge, okay? But for the topological case, you exactly get two, I mean, edge modes, exactly living at the very edge of the sample, meaning at this A site or this base site, B site. Okay, and these modes essentially correspond to these zero energy modes. So these are the three four differences. Now, the key point that I'm trying to tell by all of saying all of this, whether you calculate the winding number, which is you can calculate only in the periodic case, right? You have a block wave function and block wave vector concept in only for the periodic system. That means your system is essentially infinite. You can map the infinite system to a periodic boundary condition. So there also we distinguished the topological and the trivial case by calculating the winding number, right? For winding number, we needed the block wave function. So that's the case was for periodic system. Now for the case of finite chain, which is not periodic, how do you distinguish between topological and trivial state? Is that you calculate the energy spectrum, of course, that is one way, and then you also can see this from the wave function picture. That wave function live on the edge or wave function lives only on the bulk. So the crux is that wave function plays a very important role in distinguishes between the topological phase and the trivial phase. And this is a very important concept, and it will be important throughout this course. Beyond this course, also, when you will see there are many other things like band geometry induced correspond, I mean, transport and so on. We'll see wave function again will play a very important role in the quantum Hall states, in the anomalous Hall states, as well as quantum spin Hall, and also the fractional quantum Hall. And what will not be emphasized throughout this, I mean, this course, topology and condensed matter, there is, you have heard about the Berry phase and so on in the first class itself. So the Berry phase gives rise to a lot of transport phenomena. Two of them we are going to sort of touch a little bit. One is quantum Hall effect, and then quantum anomalous Hall effect. But there are a hell lot of other phenomena which are which comes because of the Berry phase and so on. And then Berry phase is also associated with the wave function property. It is not exactly dependent on the energy of the system. Okay, energy, of course, it depends, but they're also dependent on the wave function. So this topology and other things are actually, I mean, tells you the importance of considering on importance of understanding how the electronic wave function behaves in a system, okay, and give rise to various exotic phases which are not we are accustomed to see. So what I'm saying is that because if you see the read the Escopner means first chapter or second chapter, if you read the Dude theory of metallic transport and then Lorentz Hall effect and so on, there you only see that okay, I have electrons in the system. We have some velocity which is coming from the energy of the electrons, and we're done, right? That's how we calculate the transport responses and so on. So that's the conventional way of thinking and the conventional responses. Now, once we are in the exotic phases and topological phases of matter, here all the electrical response or the measurable transport responses are going to be dependent on the wave function as well, apart from the electronic energy. Okay, so that's the broad difference between what we have been taught and we have studied in the Ascott-Mermin level. Even if you go to the semi-classical transport in Ascott-Mermin's book, you'll only see the story of band energy playing the role, right? You'll not see the wave function playing the role in the transport. But to understand these phenomena, topology and then other phenomena, all the quantum transport that are being researched nowadays uh, are intimately connected to the wave function beyond the band energy. Okay, so I hope things are clear. If you have any question, please ask. Okay, so no questions. Okay, fine. So we can stop for today. So, so in the next two class, what I'm going to do is that so we stop the discussion of or we end the discussion of SSH model and topological insulator here. Okay, we'll come back to that topological insulator because quantum Hall state is itself a topological insulating state. So we'll understand how do we so how topology sorry quantum Hall effect or quantum Hall response is robust, how disorder plays the role in stabilizing the plateau, uh, so the interplay between disorder and then magnetic field and so on. Okay, so I plan to take two lectures for quantum Hall effect. Okay, similarly I will try to similar to these lectures, I hope quite a few things are not there in the lectures. Okay, so similarly in for the quantum Hall effect as well, I'll try to have things which is not there, or even if it is there, largely it will be there in the lectures, but some alternative perspective or some few things I'll try to cover in more details. And the same things for quantum anomalous, spin Hall, and then fractional. Yeah. So if you have any question or any suggestions, let me know before we wind it up.
Sunit, is the GitHub chain is going to be used in further topics, or is it just for uh, standalone discussion?
I do not plan to cover the type chain.
No, I'm asking
Uh,
like in the whole course, this the GitHub chain model that is
yeah,
going to be applicable.
this there is a lecture on the type chain and superconductivity and Majorana state. So yes,
That's what I'm saying. Like in let's say in Hall effect or in the later part of the classes, is that model going to be used, or was it just a standalone discussion?
I guess this was a standalone discussion actually. Type
Okay,
chain was yeah standalone. Yeah.
okay,
I
okay,
do not know. It will come back in fractional. It will be connected to, but I do not. I'm not sure that the lectures connect to Majorana and then fractional and so on and so forth. If there is any
okay,
connection, I also have to read that.
okay, okay,
But as far as the lectures now till now goes on till quantum Hall effect, it was a standalone.
okay. Okay.
Yeah,
And regarding topological insulators, so the edge modes will always be present in topological insulators.
yeah, there will always be present. They will always be present
Okay.
actually. Yeah,
Okay. So
and
like even if
actually
you say insulator, it will be conducting in the edges.
exactly. So there are edge
Okay.
state. There are states to conduct, right? You need some states
Okay.
to for the electrons to conduct, and these are the
Yeah.
states, edge states
Okay.
which conducts the electricity. And not only that,
Okay.
because they are zero energy state, it is kind of uh, what can I say? Dissipation less transport. Okay.
Okay. Okay.
So there is no dissipation for this part of the transport, the transport that is happening due to the edge state. Yeah.
Okay.
Okay. The question is, where will you share the file? So you have a Google Sheet folder, I think Google Sheet file that is being shared by NPTEL, I think. So I will upload those lectures and notes there. Okay. Okay. So the next class will be on quantum Hall. Uh, please join. I hope these lectures are useful. Okay. Thank you for joining.
Sure. Thank you. Thank you. Thank you so much.